Okay, so last time we spoke about how we can deal with uncertainty by using the Bayesian belief network basically. So in the Bayesian belief network we have a number of uh, random variables which take some values, and you have the links between the random variables in such a way that the direction of the arrow tells you that uh, uh, which node is influencing which node, and we have the conditional probability tables so that we can get an idea of all the probabilities, all the dependent probabilities that are there. And what we can do there is we can get a joint probability of anything that we want in that world basically. So now when we look at the Bayesian belief network, it's basically a static world. In other words, all the random variables will take some fixed values, and when you take those fixed values, then you can model it by using this Bayesian belief network. So for example, in the example of repairing a car, so what you are going to do is our job here is to put all the variables which will be the evidence, and then we try to see what are the dependencies, etc., and do the Bayesian belief network. But what we do here is that during the process of diagnosis or the process of repairing what has gone wrong, you are going to have a static world. In other words, whatever is broken remains broken till the entire diagnosis or the entire process is over, and then you are going to fix it. So this is a static world, but what you find is that it's not always the case. For example, if we take the example of a diabetic patient, so what do you have as evidence here? The evidence will be their insulin doses, the whatever food intake they have got, what is the blood sugar measurements, and etc. Right? And we need to assess the current state of the patient. So this includes things like what is the blood sugar level they have, what is the insulin level they have, and things of that sort. So we make a decision on this by seeing the patient's and as you do this, you will be giving the patient has some particular food intake and some insulin dose that he is going to take. So because of that, the condition of the patient keeps changing. So what you have is a dynamic problem, not a static problem. So you find that things like blood sugar levels and insulin levels, etc., keep changing over time because of the food intake they have, the insulin doses that they are taking, the metabolic activity that is going on, and on the time of day, etc. So we can say that it's a dynamic situation, and it needs to be treated as a number of time steps. So we need to see how to model this dynamic situation. And there are other such examples. For example, location of a robot. So that also keeps changing over time, and tracking the economic activity of a nation. So that steps are being taken at every point in time to improve the economic activity. So you may find some changes in it. So it's a dynamic situation, and making sense of spoken or written sequence of words. So these dynamic situations, how do we model? We need to see, because all we have done till now is done the static situation. So what we do basically is that we view the world as a series of snapshot or something like time slices. So at regular intervals of time, you do the same process again. Okay, so you'll have a set of random variables, some observable, some not, and then you need to take a particular find the probabilities, etc. So what we do here is that we assume we have the same subset of variables at every time slice, right? And then if we use xt to denote the set of state variables at time t, so you all the variables, state variables, that is the variables, hidden variables, these are at time t you have a number of variables, and et is the evidence variables that you have. So at any particular time t, you will get capital Et is equal to small et. So those are the evidences that you are talking about. So just to understand the concept, let's take a very simple example. So what happens is you have a secret underground installation where you have a security guard, and the security guard wants to know whether it is raining or not every day. Okay, so the frequency is once a day, right? He wants to know whether it's raining, but his only access is when he sees the director. If the director comes in with an umbrella in his hand, okay, then he thinks it may be raining. So that's the idea. So for each day t, you have the set et, and what does this et consist of here? The evidence. The evidence is the umbrella or not, okay, whether the umbrella appears or not, or if you call it umbrella t. And then you have the set xt, which consists of a single state variable, which is the rain, whether it is raining or not. Okay, so that is the problem that we can think of. There may be problems which involve larger sets of variables, but this is a very simple, easy to understand example that we are seeing. So for example, in the diabetes example, we may have evidence variables such as the measured blood sugar and the pulse rate, etc. Even things like BP, all these things, whatever you are measuring, those are the evidence variables. And the state variables are things like blood sugar, stomach contents, etc. Okay. So the interval between the time slices depends on your problem. In a particular problem, it may be like hourly, or it could be once a day. So you cannot really say. For diabetes monitoring, maybe it's an hourly basis. In the case of this umbrella problem which we are seeing, it's like once a day. Okay. So that is the interval between the time slices that we are talking about. So what we have is that the state sequence, okay, that is the variable xt, it starts at t is equal to 0. So you will have capital X naught, right? And the evidence will start arriving at t is equal to 1. So the state variables in the case of the umbrella problem are R0, R1, R2, that is it raining or not raining, and the evidence variables are umbrella or not umbrella, U0, U1, U2 say, right? So let us look at how we analyze this. So when we say A colon B, it means that you are taking a range of or a sequence of integers from A to B. For example, you have 1 to 3 or 1 to 5, like that. So when you say XAB, you are looking at the set of variables from XA to XB. So if you say U13, means you are taking U1, U2 and U3. So what we need to see is how does the world evolve, which is called the transition model, and how the evidence variable get their values, okay, which is the sensor model. Okay, so we have the transition model and the sensor model in this case. So if you look at the transition model, we actually want to find the probability of xt given x0 to t minus 1. So, given the earlier state variables, how do we find the probability of the present state variable, which is xt? Okay. So, now what happens is, if we say 0 to t minus 1, it's a very large size, right? So, as you go on in time, you find that 0 to t minus 1 is almost unbounded, right? It becomes very big. So, here is what we do, we make the Markov assumption. So, what is the Markov assumption? Markov assumption means you are saying that the current state depends only on the previous state, or maybe the previous two states or some such thing, right? So, it depends on a finite fixed number of previous states basically, okay. So, when you do this, this is known as a Markov process or a Markov chain. So, when you are taking only the previous variable, then it is called a first order Markov process. So, in other words, we are saying when we say probability of xt given x of 0 to t minus 1, it is equivalent to saying probability of xt given xt minus 1. So, so this is called the first order Markov process, and the transition model is p of xt given xt minus 1, and for the second order Markov process it would be probability of xt given xt minus 2 and xt minus 1. So that is how you look at it. So if you look at this figure here, so this is a network structure for the umbrella problem. Okay, so you have the transition model P reign of t given reign of t minus 1. So this is what we have here. Okay, and this is the conditional probability table, and then we have the sensor model here, which is P of umbrella of t given reign at t, right. So this is your Bayesian network structure, okay, which we are talking about here. Okay, so you are assuming that the conditional probability of reign P of RT given R of t minus 1 is the same for all t. Okay, so there is no change. So you are saying that it is a stationary process basically, and we only have to specify one conditional probability table. Okay, so the same conditional probability table can be used for all time slices where we say probability of RT given RT minus 1. So now if we come to the sensor model, the evidence variable ET would depend on the state variables, earlier state variables, that is x from 0 to t, and from the evidence from 0 to t minus 1. So this you are assuming it to be given x of t. Okay, so here also you are making a sensor Markov assumption over here, right. So you are saying that it's only dependent on x of t basically. Okay, so here we have the arrows pointing this way, which shows that the umbrella, the reign influences the umbrella. Because of the reign only you have the umbrella. So the reign is the cause and the umbrella is the effect basically. Okay. So what we have here is the transition model and the sensor model, and we also need to know how you get started on this, that is the prior probability distribution P of x naught. So once you have these three, then you can have a complete joint distribution. For example, probability x from 0 to t, e from 1 to t is equal to p of x naught into, if you take every time step I is equal to 1 to t, you have these two probabilities. Okay, so one is the sensor model probability and the other is the state model, transition model probability. So these are the things that we need to know. So the three terms on the right hand side are the p of x naught, p of xi given xi minus 1 and p of ei given xi. Okay. So this is the first order Markov process that we are looking over here. Okay, one more thing is when you are assuming that it is a first order Markov assumption, it may be true, even if it is not true. For example, suppose it depends on not one variable but may depend on two variables or three variables, whatever. You can approximately take it to be a first order Markov assumption. One example of first order Markov assumption is that suppose you have a particle, okay, which is walking along the x-axis and every point in time it either goes to plus or minus 1 of wherever it is now, right. So here obviously the next step depends only on the present step. So this is what is called a first order, really a first order Markov process, whereas here it is possible that some of the earlier values could also affect. So the assumption could be only approximate, it may not be really exact. So how do we improve the accuracy of this approximation if you have taken an approximation, right? Suppose it is an approximation, the Markov assumption. One way is to increase the order of the Markov process model. Okay, so that means you make it a second order model. Maybe a second order model will work better than a first order model. That is one. Another is to increase the set of state variables. Maybe you can use things like season, temperature, humidity, pressure, etc. Right? So these are two ways where you could try to improve this process. So you could also have new sensors, right, to measure the temperature, pressure, etc. Okay, so let us say that you are looking at the robot tracking problem. Okay, so there are two things you take into account, the position and the velocity, right? So the position and the velocity, and what we need to know is we need to calculate the new position of the robot, and the robot is battery powered, right? So suppose the battery turns off, right? So there's no charge in the battery, then obviously the robot won't be able to move forward, right? So you may have to take such variables also into account, right? So what you do is that you can include the battery T, which will tell you the how much charge the battery has as one of the variables, right? Because instead of assuming that the battery has the power and the robot can move forward, if you can also check what is the charge of the battery, right? And this charge of the battery depends on the previous battery. So battery T minus 1, it depends, and on the velocity. Okay. So, so if you do this, then you find that it may help, right? So you need to improve the accuracy by adding a new sensor for the battery level. So you can use a dynamic Bayesian network, okay, for this, which is a temporal probability model. So it's just like the Bayesian belief network, only thing is the time slices are also included in it. So each slice of the DBN can have any number of state variables and evidence variables. Okay. So you can look at it also like a hidden Markov model. Okay, so the hidden Markov model, so you can say that you could also represent it as a hidden Markov model. In other words, every hidden Markov model can be represented as a DBN, okay, with a single state variable and a single evidence variable. So we can say that the DBN can be represented as a HMM and the HMM can be represented as a DBN. So suppose when we say that a hidden Markov model is equivalent to a dynamic Bayesian network, okay, then what would be the difference between the two, right? Why do we need a DBN basically? So just like we argued in the case of the belief network, here also there actually the joint distribution, the complete joint distribution, okay, needed much more work to be done than using the Bayesian network. Similarly here, the HMM requires a lot more work to be done as compared to the DBN. Okay, so in the DBN, if the DBN transition model has 20 into 23, that is 160 probabilities, right? Whereas if you look at the HMM, it has 2 to the power of 20 states and it has 2 to the power of 40 probabilities. So we can see that obviously the DBN is much simpler to use than the HMM, even though they are analogous in many ways. So this is something like the relation between the Bayesian network and the joint distributions which we spoke of last time, right? So next is how do we construct the Bayesian dynamic Bayesian network, right? So what we need basically is the prior distribution over the state variables, that is a P of x naught, and you need the transition model and the sensor model basically. Okay. So you need to also specify what is the connection between the successive steps that you are going to have, or the successive time slices that you are going to have. What is the connection between them, and the connection between the state and the evidence variables. Okay, so here actually what has been given here is the connection. So you have the prior here P of R naught, right, and then you have range 1, so at time step 1, right, so and you have this conditional probability table and umbrella 1, okay. So this is the specification of the prior transition model and sensor model for the umbrella problem, right. So using this you can get the complete DBN which we are looking for. Now if we look at the battery powered robot, okay, what are the variables we have? The state variables will be the position and the velocity. So xt gives the position and xt dot gives the velocity, right. So here we have the x naught dot and the x naught. So x naught gives the position and x naught gives the velocity at time t naught, right. And this is influences the values of x1 and x1 dot, right, and also you have the battery at time t naught. So the battery at time t1 is influenced by that one and the velocity, right, And then you have the meter of the battery, and this meter is influenced by the battery basically. So this is the DBN for the robot motion which we are talking about, right? So suppose we look at the sensor model for B meter T, right? So battery T and B meter T can take on discrete values from 0 through 5, okay. So in the CPT you get B meter T given by battery T, okay, should have a probability of 1 if the meter is working properly, right. If it is not working, then the probability will be 0 basically. So that is in ideal conditions, but of course there will be some noise also in the measurement, okay. Okay. So now what we need to see is what happens when the sensor actually fails, right. So when the sensor fails, so what you find is that you are going to get even if the battery is fully charged, okay, because the sensor fails, you'll be getting that battery is battery charge is 0 basically. That's what you are going to be getting in such a case, okay. So what happens is that suppose the robot observes 20 consecutive battery readings at 5, okay, then the battery meter has a temporary seizure, okay. In other words, it doesn't work. We know how instruments stop working momentarily, etc. So you find that at the 21st time step, you are going to get the value as 0, okay. So according to Bayes' rule, if you take probability of P meter 21 equal to 0 given battery equal to 21, and the prediction error P battery 21 given B meter from 1 to 20, right. So what you find is that after T is equal to 23, you find that the reading returns back to 5, right. So, so it will return to 5, okay. So this is as shown over here, right. So you find that it goes down, but it returns to 5 in the next time step basically. So there is a time step when it is convinced the battery is empty, okay. So suppose it had shut down at that point in time, right. So generally what you can do is that we need to be able to handle, for a system to handle sensor failure properly, the sensor model must include the possibility of the failure, okay. And another thing is it's possible that the failure that you are looking at, okay, is not the charge at all, but it could be that there's a meter failure, okay, there's a problem in the meter that is being used, right. So if the meter that is being used has a failure, then how do we model this? So all these things have to be also taken into account. So if you have something like this where B meter, you also have something like BM broken, okay, so the meter is broken, right. If you have something like that, then if there is a failure, then you can actually maybe predict that the meter is broken and not that it's because there is no charge in the battery. So we can see that all these things make a lot of difference in what we are doing. So let us look at how inference actually is done. Okay, so you'll be starting with the times 0, and then you'll be keep on replicating slices. So you have slice 1, slice 2, slice 3, etc. Okay. So this technique is called unrolling. Okay, so you'll be unrolling one slice at a time. So once you do that, you can use any type of inference. So we saw how we carry out inference. Okay. Okay. So it would be something like this, right? So you have rain at 0, then you have rain at 1, rain at time 2, rain at time 3, rain at time 4. So what we are doing is unrolling can be carried out, okay, and slices can be replicated as you go on. So what happens is that instead of having so many time steps as shown here, you can do what is called the summing out. So when you do the summing out, so you're eliminating the earlier slices. Okay, so at any point in time, you'll have just 1 or 2 slices that you're talking out. So this modified algorithm, where you're using variable elimination and summing out, it keeps at most 2 slices in memory at any time. Okay, so you have starting, you have slice 0, and then we add slice 1, and then we sum out slice 0 and we add slice 2, etc. Right? We add slice 1, then sum out slice 0, then we add slice 2 and we sum out slice 1, etc. So you find that you don't have to keep the entire dynamic network for all time slices at any point in time. Okay. So we can say that the maximum factor size is order of d to the n plus k, where d is the domain size of the variables and k is the maximum number of parents of any state variable. Okay, so you see which state variable has the maximum number of parents, so that is k. So you use k over here basically. So what happens is that even though if you use the HMM, okay, we got over here order of d to the n plus k, but in the case of HMM you will get order of d to the 2n. So obviously it is much better than using the HMM, but still, even though we can use DBNs to represent very complex processes, we can't reason efficiently and exactly about those processes. So what happens is, again, it's quite big. Okay, so that's the thing. So what is generally done is that some type of approximate methods will be used instead of that basically. Okay, so this was about the dynamic belief networks. So we'll stop at this point in time and continue in the next session.